Okay, it's really dark in here, but the reason for that is I have a Voltaic cell behind me that I built as a demo for this video, and it can power a light, but it's a very dim light. So check this out. If I connect the two cells together, see, there you go. Let's see if I can zoom in a bit on that. Check that out. How cool is that? Most batteries you've encountered are some kind of a voltaic cell, whether they're a small AA battery or the big 12-volt lead-acid battery in your car. But what exactly is a voltaic cell, and how does it work? There are many processes at play, but perhaps the two most important are intermolecular forces and redox reactions. First, let's talk about intermolecular forces, or IMFs. IMFs are interactions between molecules, and in some cases between individual atoms, as we will see. There are four main IMFs. The first of these forces is the London dispersion force, or LDF. It is a weak attractive force between molecules. All molecules experience LDFs to some degree, and it's theorized that the cause of the force is the creation of instantaneous dipoles around molecules. Imagine you have an atom like helium. Its two electrons orbit it in constant motion. Sometimes they are on opposite sides of the nucleus.
And beneath a man, we find his nucleus.
Nucleus?
Yes.
And sometimes the electrons are on the same side. When this happens, just for a moment, it creates a separation of charge, a dipole, slightly positive on one end, slightly negative on the other. These temporary dipoles can cascade through materials, creating a very weak cohesion. The next force is the dipole-dipole force, or DDF. This force occurs between polar molecules, such as water, and it is responsible for water's surface tension. It's why water is often called a universal solvent. Acetone is another example of a polar molecule. The oxygen is highly electronegative, and it hoards the electrons in its double bond with carbon. The molecule overall is asymmetric, and the result is that there is a permanent slight negative charge centered around the oxygen, and a slight positive charge on the opposite end of the molecule. When two of these molecules approach each other, their dipoles orient, and they attract. The ability for two liquids to mix is called miscibility. Oil is nonpolar, while water is very polar. The result is that the water molecules feel a greater attraction to each other than they do to the oil molecules, and the two will separate. Hydrogen bonding is a very important kind of dipole-dipole interaction that is even stronger than a typical DDF. This happens when hydrogen is bonded to a very electronegative element. Hydrogen only has one electron to lose, and it can't compete for the electron like larger elements can. The result is a dipole that represents a near-complete positive charge. There is one more force that we'll talk about, and it is particularly relevant to voltaic cells. That is the ion-dipole forces. Ion-dipole interactions happen between dipoles, like those in water, and ions, like sodium, that carry a full positive charge, or chlorine, that carry a full negative charge. This is a crystal of table salt under 100 times magnification, an ionic compound comprised of the cation sodium and the anion chlorine. When ionic compounds like this are added to a polar liquid like water, the dipoles of the water molecules attract the ions in the compound. It is this attraction that causes materials like table salt to dissolve in water. And this attraction plays a part of the function of a voltaic cell. In these two beakers, I have two different solutions. In the left beaker, I have a 0.5 molar solution of magnesium sulfate, and in the right beaker, a solution of 0.5 molar copper sulfate. When I place a salt bridge filled with a 0.5 molar solution of sodium nitrate between the two beakers, the circuit is completed and the LED between the anode and the cathode is powered. The driving force behind a voltaic cell like this is what is known as a redox reaction, because it is a reaction where one of the products or reactants gets oxidized while another gets reduced. In simple terms, a redox reaction is any reaction where an electron is transferred from a reactant to a product. The reaction powering this voltaic cell is between copper and magnesium. Magnesium is more easily oxidized than copper, and as a result it donates its electrons to the aqueous copper ions. This means the magnesium gets oxidized and the copper gets reduced. For every atom of magnesium oxidized, 2 electrons transfer to a copper ion that gets reduced. Under standard conditions, the potential of a voltaic cell can be calculated by this formula. This formula states that the potential energy of a cell is the difference between the potential energy of the reduced species and the potential energy of the oxidized species. Let's calculate the potential energy for this magnesium-copper voltaic cell. In our reaction, the magnesium is oxidized, losing 2 electrons. The potential for this reaction is negative 2.37 volts. And the copper is reduced, gaining 2 electrons, which has a potential of 0.34 volts. Which gives us a potential of positive 2.71 volts under standard conditions. In reality, we get a much lower voltage. This is due to a number of factors: inefficiencies in the cell design, resistance in the wires, a non-standard environment. So instead, we use the Nernst equation. The Nernst equation is used to determine the cell potential for varying concentrations and temperatures, although a simplified form is often used. Here, n is the number of moles of electrons that gets transferred, 2 in our case. However, because Q is the log of our concentrations of products over reactants, and both concentrations are approximately 0.5 molar, that means the log of Q becomes 0, and our actual potential should match our ideal potential, but as we saw, it doesn't. So there are more factors at play when determining the actual voltage of a voltaic cell. Finally, let's talk about cell design. That little thing, the tube you see going between the cells, is an ion bridge. In order for these cells to function, they have to be able to equalize the ionic charge between each cell. The ion bridge is filled with an electrolyte, in our case sodium nitrate, that dissolves into 2 spectator ions. They are neutral overall and won't take part in the chemical reactions taking place, but they serve as a means for ionic charge between the cells to neutralize. The electrode in the blue-colored beaker is made out of copper. This is the cathode. The blue coloration in the solution is copper sulfate. It's these ions that are being deposited on the cathode during the redox reaction. In the other beaker, we have a magnesium anode. The solution in the magnesium beaker is magnesium sulfate. As the reaction occurs, the concentration of magnesium sulfate will increase as the anode gets eroded away. As the magnesium anode gets oxidized, its electrons travel along the wire, through the LED and powering it, and to the copper cathode, where they neutralize copper ions.